All right, we're going to try some examples now with the rotation. So remember from previously, we said that the relationship between angular position and distance, or angular displacement and displacement, is going to be S equals theta times R. Okay, so the key to this whole chapter is getting the idea that you can take any angular momentum, angular quantity, multiply it by the radius, and get a linear quantity. At the same note, you can take any linear quantity, divide by the radius to get the angular version. Okay, so in this scenario, we have a drum that's being rotated to lift up this object. Okay, it says this drum has a radius of 50 centimeters, or we'll say 0.5 meters, and we're asking how many revolutions of the drum are required to raise the bucket to a height of 20 meters. Now revolutions, that's how many times it needs to be rotated. Okay, well we know that one full rotation, or one revolution, is equal to 2 pi radians. Okay, and so if we can find the number of radians, we can easily get the number of revolutions. Well, it's going to come to this right here. Okay, so we're going to use this equation. We're going to say that, okay, it's going to go a distance of 20 meters. Okay, so we want to find the number of radians, or the angular displacement, and we know that the radius is 0.5, so we're going to put our 0.5 meters there. Okay, so we'll divide this over, alright, and 20 meters divided by 0.5 meters is going to give us 40 radians. Okay, now the reason why this is radians is because this is kind of like, if you think about this being our radius, we're saying that it's 0.5 meters per one radius, okay, or per one radian. So when you divide that over, you end up multiplying the radians up there and canceling out the meters. So anyway, we get 40 radians, but that's not what we're looking for. We want to know the number of revolutions. Well, if we say 40 radians divided by 2 pi, that's going to give us the number of revolutions. So that's going to be 20 over pi. And so we get about 6.37 revolutions. So what that means is, in order to raise this object up 20 meters, we're going to have to rotate this drum about 6.37 times. Okay, so now we have kind of a second example to use that equation again. You have a bicycle tire. We know its radius is 25 centimeters. And we know that the wheel is going to make 400 revolutions. The question is, how far will the bike have traveled if it's going to rotate 400 times? Okay, and well, we use the same equation that allows us to relate angular displacement and distance to the radius, okay, but I'm going to let you guys go ahead and do the rest of it real quick. So you've gone ahead and found your distance. Let's go ahead and do it now. We know that the radius is 25 centimeters, or 0.25 meters. Okay, we have an angular displacement of 400 revolutions, but I can't take this and put in for this, because this equation only works if my angle is in radians, because it's taking the number of radians and multiplying it by the number of radii to get your distance. Okay, so 400 revolutions times 2 pi to get radians is going to be 800 pi radians. Okay, and so we'll say S equals 800 pi times our radius of 0.25 meters, and so we'll travel a distance of 200 pi, which is going to come out to be about 600 28 meters. Okay, so if you're riding a bike with 25 centimeter tires and those tires rotate 400 times, that means you've gone a distance of 628 meters. All right, so now that as we continue, we're going to move on from talking about angular position and angular displacement to angular velocity, okay? And there's one other thing we want to mention to go with angular velocity. Something else that we can talk about that has to do with how fast something is rotating is frequency. And frequency is equal to 1 divided by the period of rotation. Remember that this is just how long for one rotation. It can also be found by taking the number of rotations and dividing by the amount of time. Okay? The units for frequency is 1/seconds. Okay? And we call that hertz. Okay? Now, for angular velocity, okay, that's going to be the number of radians divided by the time, okay, or the number of radians per second, okay, and so you can see that you would be able to convert between frequency and angular velocity by converting your radians into rotations or your rotations into radians. Okay, there's also one more equation I want to show you, and it's that the angular velocity is equal to 2 pi times the frequency. Okay, it's also equal to 2 pi over the period. Okay, and so we'll get into these equations a little bit as we go. Okay, so now I'm going to show you this example here in which we have a circle. Okay, you see it's going to rotate for you. Now the question I have is, in this circle you have points A, B, C, and D. Of those four, which one has a greater angular velocity? So which one is rotating faster? Okay, go ahead and make your prediction, and let's go ahead and see. Hopefully what you saw is that the angular velocity for all 4 points was the same, because each of the points made the same number of rotations in the same amount of time. Okay, now the time actually was 2 seconds. Okay, they made one rotation in 2 seconds. Okay, or 2 pi radians in 2 seconds. So the velocity, or the angular velocity of each of those points, was 3.14 radians per second. The frequency, which is just the number of rotations divided by the time, would have been 1/2 or 0.5 hertz. Okay, so let's look at this one more time. This time I want you to decide, of these 4 points, which one will have the greatest velocity? Which one will be moving the fastest linearly, okay, at any instant? So let's go ahead and rank the 4 based on what you think will be moving the fastest and the slowest. So let's go from fastest to slowest, rank them based on what you think will be going fastest and slowest. Okay, now let's go ahead and watch and see. All right, let's show it one more time. Hopefully you saw that A was going the fastest, then B, then C, and then D. And the reason why, so just like we have this relation S equals theta times R, we have this one too, that V is equal to omega times R. All four positions had the same angular velocity, but as the radius increased, so did the velocity. And so point A had the largest radius, so it was going the fastest. Point D had the smallest radius, so it was traveling the slowest. Okay? They all were rotating at the same rate, but the points were moving at different speeds. Okay, I'm going to show that video one more time so you can see it one last time, and that'll be the end of this video. Okay, so let's take a look at it one more time. Pay attention to that all four of these are rotating at the same rate. They're going to complete one rotation at the same amount of time, but point A is moving faster because it has a greater distance to travel than D to get all the way around. Okay, so here we go. Alright, and that will be the end of this one, so I'll see you guys later.